Okay, let's start our afternoon sessions. Andre is chairing, but he had to run off for something. So I have the great pleasure of introducing my PhD student, Ekin Akyurek, who's at MIT, has been doing a bunch of work, most recently on, just kind of understanding both empirically and theoretically the kinds of computations that transformers can perform and other neural sequence models can perform when doing in-context learning. And I'll let him take it from here.
Yeah, good afternoon, everyone. I will try to explain how transformers learn new structures in context. And I will share two different problems to analyze in context learning and show that these problems can guide us to design new model architectures. Every month, I become more worried about prompting. I actually don't know whether my deep learning skills will be relevant in the future. I was working on this ARC challenge before they announced a $1 million prize on it. And in this challenge, the model needs to solve questions that requires an abstract reasoning. The model needs to understand what transformation applied in the given demonstrations. Then it should predict the test example correctly. I was investigating language model baselines as usual. If you encode these examples into text and feed it to an open source language model, they basically fail. Even if you fine-tune on the training set, it will be around 2 to 3%. Private models like GPT-4, with just zero-shot prompting, gets 11%. And recently, O1 gets 21% in this task. I was also looking at neurosymbolic solution where you ask GPT to write the transformation as a Python code, and I could get 1 to 2%. However, this blog post came out recently, and by using the same methodology, but they sampled thousands of Python programs and used very detailed fifth-shot prompts that includes chain of thought reasoning, and they could get 50%. So you can get 50x improvements by guiding model with fifth-shot learning and sampling more. And this is not one of a case or not just my bad prompting skills. And I was reading this paper from Meta, and here's a statement saying that their prompt improves their results almost 3 times, from 25% to 65%. Well, your first instinct is to say this is black magic or alchemy when you have 50x or 3x by just changing a small text in your prompt file. And this is definitely not the first time we are feeling like this. In 2017, Ali Rahimi gave an interesting talk criticizing the state of the deep learning research at the time and draw analogies to alchemy. And in this context, alchemy refers to pseudochemistry in archaic times, like mixing materials together, hoping to produce gold or healing things, etc. And his argument is that alchemy is okay if you want to produce, let's say, a metal for a sword, but it's not okay if you want to do healthcare-related application. And he argued that our understanding of deep learning is similar, and we are essentially practicing a form of modern-day alchemy, and it is dangerous. This kind of skepticism arises when there's a significant shift in the field, and a caricature of this shift could be a switch from shallow model libraries to deep model libraries in our code bases. So we start to worry and complain when the state-of-the-art system exceeds our understanding. But the same year Rahimi gave this talk, the transformer paper is also published. And this paper is even more revolutionized the field and generated the landscape of research that we are doing today here. After 7 years, we have even more alchemy to understand. And interestingly, the tables have turned around. Now the deep learning student becomes a little bit rigorous and blames the computer science undergrad who prompts well and beat their scores. I took my first AI class in 2017, and this change, like seeing this change real life, teach me these 2 statements. Everything starts with alchemy, and it is beyond the size at any point, by definition. And we should just embrace and carefully invest and experimentally work on it. But we should also understand why and how it works, because only then we can know the limits and dangers. One of Ali Rahimi's point, actually this is a good point, we learned that the real alchemists couldn't possibly produce gold by just mixing different materials, but we could learn this after 2,000 years once we have the modern chemistry. So it may take years, but for every new alchemy, we eventually get a better understanding. We now have more studies on why deep nets work, what are the error bounds and their limits, and we have robust learning curves that we can predict the future training grounds. But when it comes to prompting or inference, we often not do the hard work and just do the guessing. So we should understand the alchemy of prompting or language model inference time capabilities in general. And today we will focus on in-context learning specifically. You may wonder, why do we even treat these two things as it is the same category? One is learning with gradients, and the other is a fixed network and inference time paradigm. But let's look at this plot. Can you guess what this is? This is your everyday pre-training curve. On the y-axis, you have the negative log likelihood, and on the x-axis, you have the number of tokens trained. Can you guess what this other plot is? And this is produced by few-shot prompting a language model on different question answering benchmarks. It again shows the negative log likelihood on the y-axis with respect to the number of examples provided in context. Both of them are same kind of curves obeying power laws. The model somewhat learns linearly with the log of the input length. So if you are able to produce a whole set of theory for the left plot, why don't we produce some theory or analysis to understand the curve on the right? And in this talk, I will share the two studies for few-shot prompting, specifically to figure out the in-context learning capabilities of transformers. But I want to note that there are other phenomena we still don't understand. For example, incantations, where you say model that you are smart, they started to perform better. But I am hopeful that we will have like a natural understanding of all of these at some day. So let's start the content. So to concretize what I mean by in-context learning, we have a language model trained on a large corpus to predict the next token in every context. Then we take this trained model, provide few examples from a task in the input. For example, here we have English to French translation. You could have semantic labeling of sentences. You could have even polynomial regression. Then after the last example, the language model starts to work as it is a classifier, and it can predict many other input queries correctly for any of these tasks. But in-context learning is not just a classification task. It's not just for classification tasks. You may also imagine generative tasks, like a string puzzle that I generated here, or in-context copying task that is sometimes called associative recall, or even learning a new language from a grammar textbook. This is studied in Gemini paper. So the big question is understanding how the models succeed in each of these cases with a text prompt like this. In other words, how we can replace the whole deep learning pipeline that requires thousands of labels and computationally expensive training with gradient descent. This is a hard question, and to answer this for each task, we could come up with different analysis, but instead we can develop model problems that we can study rigorously and hope to learn from them. So rest of the talk, I will discuss and share results on these two different problems to study in-context learning in isolation. Then we will try to understand how transformers solve each of these learning problems. And finally, we will use our understanding in these problems and try to improve language modeling. And these are collaborative efforts with co-authors from MIT, Google, and Stanford. And I will first present a summary of in-context linear regression problem, and later I will share the recent language learning problem that we proposed. These model problems, in my opinion, are analogous to model organisms in biology. So biologists also study model organisms before studying humans. So they are small-scale organisms that can reproduce quickly. They are in small size, and most importantly, that has some structural similarity to the humans. And AI researchers, our challenge is understanding these complex language models. And on top of this, each different in-context learning task can require different analysis. So to address this, or at least start this question, we propose model problems that are easy to replicate, easy to train, but we need to make sure that these problems are also resembles to real in-context learning examples. Maybe because it's the simplest problem in ML, and we know a lot about linear regression, many people, including me, worked on this linear regression problem as a model for in-context learning. You may consider this maybe as like C elegans of linear regression research, in-context learning research. And let's remember this few-shot translation example. This is a single word version. So the model presented examples from a mapping, in this case, English to French, and it needs to figure out this mapping on the fly. Now, instead of this mapping, consider a linear regression problem, and we ask if we can build a model that can observe sequence of input-output pairs that exhibits a linear relationship. And we want model to infer this relationship on the fly. And at the end of this sequence, we want model to be able to produce correct outputs from the inputs. And importantly, we want models to in context learn any linear function, not to just this function presented here, but any linear function from a class of linear functions. So when studying these problems, we train a small transformer model from scratch on some example problem instances. So we first create a training set by sampling different linear functions, and then we sample inputs, and then we map them to the outputs. So these data points will be our few-shot examples. Then from a set of these linear functions, we will train a transformer language model to predict the next target given the previous examples. And we evaluate whether the outputs get close to the ground truth after seeing enough number of examples. And note that this is a language model, but it takes continuous numbers. So we can summarize all of this with the loss function here. Language model takes a sequence of continuous vectors where in-context example presented one by one. And at the end of this sequence, we want model to produce the last output vector. And we can make it a bit more concrete by just putting the outputs in place. And we eventually want language model to minimize this loss function by inferring any W from these structured inputs. So in our ICLR paper, we show that we can manually construct a transformer that is actually capable of solving this problem during inference. And this hard-coded language model simulates gradient descent. Given the input examples, it predicts the final output with an estimated weight vector. And this weight vector, W hat, is computed in the hidden states of the model from the previous examples. We also show that if you have more layers, then transformer can also compute the optimal solution to this problem, which is the ridge regression solution, by simulating an iterative algorithm. All of these construction is to show that learning with a fixed LM is possible with a few layers of a transformer. So how do you show these? If you show a transformer layer can do a basic linear algebra, then you can show all of this is possible. And after the talks in this workshop, this shouldn't be any surprise. But maybe different than previous work, for example, the RASP language, we define continuous operators instead of discrete operators because we want to do linear algebra. And once you define this operator and show that transformer can run this operator, then you can use this to build any linear algebra algorithm you want. But we can actually try to interpret what does transformer do in this task when you train with data. Do they find these solutions? Do they find gradient descent or ridge regression? And our manual constructions required a certain number of layers and certain number of hidden size, but do we get this scaling behavior in the real transformers? We experiment by changing the hidden size and depth of the model. And on the x-axis, we do this. And on the y-axis, we show the squared error distance between transformers prediction and algorithms prediction. And here, the colors specify different class of algorithms. The blue lines are the SGD variants, and the orange lines are ridge models, and the green line is the least square solution. In both cases, we see that the best fit algorithm changes as we scale the model. So the shallow models, like one-layer models, are more close to SGD-like solution. And then the mid-size models doing some ridge regression, there's no noise in this data. So, and then finally, if you have enough number of layers of enough number of hidden sizes, you see that they find optimal solution, which is the least square solution. And this model sparked a theoretical curiosity, and many people perform different analysis on transformers, such as convergence, like training dynamics, phase transitions. And for example, now you can show that actually the gradient descent solution is the optimal solution for one-layer linear attention model. But this linear regression problems looks very different than the kinds of prediction problems that language models needs to solve. So they are continuous, they are single step. So what this tells about the language models? Yes.
Are there any experiments that try to, so let's say you train something on some linear data, and then you compare the performance curves on some polynomial regression context. It still finds the same thing? The best model within the class that you force it to do? I mean, it's still doing great in the same or not?
They didn't try like the out of distribution experiments, but people try like training with normal and then trying with sparse linear regression problems. I'm trying to see if there's something similar. Yeah, I think we didn't try, but as long as the distribution will be different. But yeah, that's a good question. Let me remember. Yeah, I don't see any paper, but there's a lot of distribution shift papers, like where you sample from one region of Gaussian or one region of the XY axis, but you train a test on the other regions. So there's some like out of distribution generalization experiment.
So I actually thought there is evidence that would not work. Like even if you change the distribution from Gaussian, the priors of the W to some other.
Yes. Yeah, so like I think one thing that I didn't show, like when you add noise to this task, the model does the Bayes optimal algorithm. So it does ridge regression, where the lambda parameter is optimal for that noise in the data distribution. So yeah, I think it shouldn't work, but that's a good question. So to close this gap, like these linear regression doesn't look like language, and to close this gap, people also studied associative recall or in-context copying task, which looks more like language. And this associative recall task is a simple retrieval task. We ask models to learn a simple map from examples on the fly, and you can think this as a phone table where each number matches with a person, and the model needs to copy the correct number when an existing name appears. And people use this as a benchmark in recent state space models. But these problems like show that transformer can in context learn some novel functions, but are these problems structurally similar to the real in context learning examples that I showed earlier? First of all, they have non-structured inputs and outputs. So each input and output is a single time step or single token, but the translation or any other real language example will have multiple tokens in the input and output. And second, these model problems do have deterministic transition functions. Each output is a deterministic function of the input in the ground truth data, but the real language in general probabilistic. So for example, here we might have multiple translations for the word cheese for some languages. So our model problems actually come from structurally very different generative process. So what should be a good model for in-context learning? And we realized that we can close this gap by using in-context formal language learning as the model problem. We can also show that this is a natural generalization of these existing problems. And in this problem, we will ask model to learn generate strings from a probabilistic regular language after seeing some number of samples from it. And unlike other problems, the models here need to in-context learn complete generative process, let's say a hidden Markov model-like structure, instead of a deterministic mapping. Let me briefly explain what this problem is. And in each example in this problem, we have this state machine that generates a language. And you can sample the edges, like you can traverse the edges in this state machine and sample the first string from this language. You can sample another string, and you can sample another string, and this will be your first example. And once you have such collection of languages and samples from them, we again train a language model from scratch on this task to predict the next character as usual. But to succeed in this task, the language models now need to infer a novel state machine from examples to be able to predict the next valid character. Before going to results, we are interested in this problem because I think it encompasses a lot of different problems in it. So for example, this associative recall problem is also can be expressed as a finite state machine, because once you have a fixed number of keys and values, you can write the state machine and then the samples will be associative recall examples. And there's also a copying test provided in the Repeat After Me paper, and they measure models' ability to copy the prompted input. You might think this is a very easy task, but some state space models fail on this. And this is also a very simple language learning problem because here each language only has one string, which is A, B, C, D in this case. So I show how this new model problem captures the features of ICL that we want and how it relates to the previous examples. And now I will move into the results, and we will first see how this problem differentiates different architectures. And then we will try to uncover why transformers are very good at this language learning task and how they solve this problem. And after these analyses, I will try to improve transformers a little bit further. And we will start by evaluating the performance of architectures one by one. And here's our learning curve for transformer. So we measure the total variation distance on the y-axis, and on the x-axis, we have the number of training examples. And to calculate total variation distance, what we do is we get the next token probabilities from the model, and then we get the ground truth probabilities from the language itself. And then we just take the L1 distance between these two probability distributions, and this will be our variational distance. Okay, so we will look at now other models. Let's first compare the linear transform model and a slightly different version called RedNet. These models do not have softmax layer normalization in their attention model. So as a result, you can express them actually in recurrent forms. And as you can see, if you just remove the softmax layer, the models get immediately worse than transformer. And you can also look at modern recurrent models like Mamba and GLA, which is very similar. And we find that they perform similar to the linear transformer, but maybe Mamba is a little better in the low resource. And again, previous work showed that these models are actually very similar to the linear attention. And the convolutional states models like Hyena, like H3, performs worse than linear attention variants. And S4 is the worst model here, and S4 is also the only linear time invariant in this plot, so it is kind of expected. And we can also look at the LSTM, and LSTM is also performs pretty worse. So somewhat transformer is the best model here by significant margins, but we want to understand how it solves this task, and we want to learn from it. But maybe before going there, if you look at this associative recall task, like you can see that the differentiation between the models are less clear here. So once you have a correct test, then you can differentiate models better. We can also do another check for this problem, which is it will be matter if this model in this model problem, the models also have this power law curves, like when the negative log likelihood reduces linearly with the log of the input length. And in the in-context language learning problem, we see exactly this linear reduction in the loss with the number of characters provided. And we also look at two classes of algorithms. One is n-grams and the other is hidden Markov models for this task. And we find that the best algorithm is actually 3-gram. And then second best is hidden Markov model trained with Baum-Welch algorithm. The details are not important. And then we have this 2-gram model. And note that these algorithms are not trained with data. We just fit them into each test example separately, and we predict the next character with them. So if you have this associative recall, what we do is we have this like n-gram table, let's say 2-gram, and then we predict the next character based on these 2-gram probabilities. And you can see that many state space models are actually worse than 3-gram, and most importantly, transformer is still best here and doing something different than these algorithms. So the next question that we look at is like, can we understand how transformers solve this, and can we learn from this analysis? So in the previous plot, we look at how each model or algorithm is close to the ground truth. But to get more intuition, we could also look at how they close to each other. So here we look at pairwise distance between transformer and other algorithms. And you can still see that the 3-gram is more close to transformer than any other algorithms here. But we know it's not exactly 3-gram, so we want to understand like what it's doing exactly. So what we did is we take the n-gram features and we feed it to an MLP model, And then we train this MLP model to predict the same task. And what we find is this hybrid model, which is using n-gram features and kind of doing a post-hoc normalization to n-grams, but it's a learned model. And then it kind of explains transformer better than all other candidates here. Another interesting result that we find is actually shallow transformers, again, is doing something different. So if you have two-layer transformer, what we find is it is more close to 2 gram than 3 gram. But the difference is not like super high, but still like it is different than the actual transformer that we trained, which has like 8 layers. So we had lots of probing experiments to understand whether these n-gram counters inside of this model, but for the time, I am skipping them, but we can look at actually attention maps of this transformer and try to understand the algorithm that it tries to implement. And here we visualize the attention of some attention maps from 8-layer transformer, and we have like layer 2 and layer 3, which is kind of boring. They're like every token looks at the previous token, but in layer 5, there's an interesting structure that we find. And let's look at it more closely. So we zoom into a specific row and columns in this attention. And this is the row that shows where this last H character attends to other previous characters. And what we find is it attends to characters that comes after NH. It comes after the same prefix, like same 2 gram prefix. So if you look at this attention, you can see that everything attends to the tokens that comes after NH. For example, it doesn't attend tokens that comes after H. So it's doing this like 2 gram match and then attends based on that. Actually, we can analytically formulate this n-gram attention where each token attends based on n-gram match as this logical formula. And if you set n equals 1 here, that will be this induction heads pattern. And these kind of induction heads, or what we call 1 gram heads here, are also found in real language models. But here we see a higher order version, or a long prefix version of it, which is 2 gram heads. So why do we want to understand these like algorithmic capabilities at the first place? Because we want to get better control of them and get a better versions of them. So from these intuitions that we gain from this task and the solution, we artificially construct such static attention heads such that they actually implement this attention from scratch. So what we do is like we fix the attention map based on this n-gram formula, and then we build this head that only has this W learnable parameter, the W0 as the learnable parameter. And then you can kind of inject these heads into either your multi-head attention as additional heads, or you can put them as intermediate layers to any model you have. And when we added these heads or layers to the other models, what we find is they just match the performance of transformer. The lower is better here. So if you add this 3 gram head, they immediately become as good as transformer. But maybe another important result, the induction heads, like the 1 gram heads, are actually not enough to get to the transformer level, at least in this language learning task. But okay, we understand these like models, how they learn this in context, how they in context learn these new languages. But is this something that we can use in like real language or real language models? So what we did is actually we did this experiment with actual language modeling task. So we added these heads into different models, and we pre-trained them on actual language modeling corpus. So we take this SlimPajama corpus with like 7 billion tokens, and we train 340 million parameters models as like this is the most we can do in academic setup. And what we find is like whenever we add these heads into the model, with the so all of these models has the same parameters, and whenever we add these heads, we see the improvements. But if you look at again, like if you just add 1 gram heads, you see significantly lower improvements. But if you add all these different n-gram heads, you get like this 2 to the sometimes in the transformer, it's the most improvement. We get like 6.7 improvements. But as Stella said, like in the talk, I think we should do this like in different scales and see how this scales up. Yeah. So what could we do better? I I think the empirical data for different real tasks is more valuable than anything. And we should do these real analysis on different tasks and see how the model handles these tasks. And interpretability in the wild for language models here is like much needed. So Eric Todd has this great paper that shows when you prompt these models with these few-shot tasks, you see these like test vectors built up in some layers of the model. And he shows the causal effects of those test vectors. You can transfer them to like any like same model without few-shot prompt, and you get the same scores. And in our synthetic problems, the pre-training data and the inference data has the same distribution. Let's say we sample linear functions from Gaussian. The inference we also sample from Gaussian. But there are other works that actually controls this pre-training distribution, and where they have different distribution, and they also see still the in-context learning effects. Well, we show that like you can improve in-context learning by inserting these n-gram heads. What we do is essentially giving test time power to model so that they can run these algorithms for free. But these are kind of essential alternative ways to increase test time compute, to what Noam Brown today said. But there are probably better ways to do this. For example, this recent test time tuning model does inject gradient descent into model. And so every updates there looks like gradient descent. This is also very similar to Schmidt-Huber, like old papers, like Fast-Weight Programmer's paper from Schmidt-Huber. But all of these architectural changes needs like lots of tests and like see whether they scale. So we need the scaling versions of these improvements. So I show these two studies like with linear regression and language learning. And we found that transformers are implementing like these n-gram circuits, and therefore they are better. And we showed that if you insert these n-gram circuits into other models, they also become as good as transformer. And yeah, I think that's it. And thank you so much for listening.
Thank you. Super cool presentation. For the in-context language learning task, is the n-gram solution optimal in some way?
So there's this. So the Bayes so in the linear regression, the Bayes optimal solution was clear, ridge regression. In this language learning, you need to enumerate. I don't know the optimal like algorithm to calculate the optimal solution. So you need to do this like Bayesian posterior calculation by just enumerating everything. But there's a thing like if you sample regular languages in a way that is not great, then you might end up more n-gram-like languages. So there's a paper called ML-Reg test that shows that like when you sample the way that we did, it's actually more n-gram-like. So that's why I think one reason that like n-gram is optimal, kind of optimal here, is the way that we sample. But it's still not the optimal solution because transform is doing better than 3-gram or all other models.
So if it's not optimal and transformers are doing better, what do you think is the intuitive reason for why the n-gram heads were able to increase performance that much?
But n-gram heads increase performance of other models, and they become as good as transformer. But other models already also have this like MLP layers on top of it. So
okay,
yeah, maybe n-gram plus some MLPs kind of do the optimal solution here.
I see what you're saying. Thank you.
So you talked about so in the context of like linear models, we can talk about how the linear regression. We can talk about how well the linear regression explains the variance observed in data. You use like language that's somewhat similar to that when talking about using n-grams to like how closely models follow n-grams. Is there some kind of thing analogous to R-squared that explains like that can characterize like how much of the behavior of the model you're capturing, or is that like a kind of loose concept?
I'm not sure if I understand. Sorry. Can you repeat?
Is it a function of the sentence distribution, or is it a function of something the model is learning? Is kind of the question.
Do you like a goodness of fit metric for when you're talking about like, oh, you know, this n-gram model behaves like a transformer?
Oh, like how do we measure the, like when we say the transform is doing n-gram-like solution, we just look at the outputs and the distance between the outputs.
Okay.
I'm not sure if I answered the question. Sorry.
But you don't have like a goodness of fit metric or something, just R squared.
Yeah, no, it's just like, oh, like for it's just cross entropy.
Okay.
Yeah.
So when these models follow the power law, right, does that mean that they're learning very efficiently? Is that kind of an indication that they're learning efficiently?
I think the power law is just like how efficiently current models learn. Like for pre-training, we have this like power law, and then for in-context learning, we have power law. And what like in our like language learning problem, we also ended up with power law. So basically, it's just to show that this task also induces this power law behavior. But I'm not sure if it's the best way to learn these languages.
And you looked at this L1 distance, right?
Yeah.
When you were doing the comparison. What led you to choose the L1 distance? There are other distances that you can use.
Yeah, you can look at cross entropy as well. I think this is just symmetric.
Like here you're comparing two distributions, right?
Yes.
So, I mean, normally people look at divergences or...
Yeah. So it's just like how divergences sometimes have this like infinities and also not symmetric.
Yeah, but you can do JS divergence.
Yeah.
You can do other
So yeah, you can do. I actually had the cross entropy versions of these plots, and they also like very similar.
They're very similar.
Yeah, it doesn't change much.
Cool.
Thank you.
Well, thanks again. And we'll resume at 3. We have, I think, a virtual talk from, say, 1 minute.